Welcome back, everyone. So in the previous two videos for this chapter, we talked about two gas laws that involve pressure, volume, and temperature. The first one was Boyle's law, and with Boyle's law, we learned that pressure and volume are indirectly proportional, specifically P1 V1 equals P2 V2. Charles' law involved volume and temperature of a gas. And we found that as the temperature of a gaseous sample increased, then its volume increased. So in this combined gas law, that's essentially what it is. It is a combined law of Boyle's and Charles's individual gas laws. And so hopefully you can see in this little blue square, you could actually pull out Boyle's law and Charles' law if you needed it to. You could see this top part of the equation is just Boyle's law. This part of the equation that I'm circling with volume and temperature is Charles' law. So since they both have volume in common, we can combine them into this combined gas law. So the combined gas law is P1 V1 over T1 equals P2 V2 over T2. And that is assuming that number of moles of your sample is constant. So one way we can use the combined gas law is in a problem like this. We're going to talk through it and actually do it on the next slide. So we have a sample of gas, has an initial volume, so I have a V1 of 158 mils at a pressure, so we've got a P1 of 735 millimeters of mercury and a temperature of 34 degrees Celsius. So we have an initial temperature, but remember with all of these gas law problems we have to convert to Kelvin, so we'll convert this to Kelvin in the next slide. But we have an initial volume, an initial pressure, and initial temperature. Next sentence says, if the gas is then compressed to a new volume, so we now have a V2 of 108 mils, and heated to a temperature, so we have a new temperature, 85 Celsius. Change that to Kelvin in the next slide. What is the final pressure? So we're looking for P2 in millimeters of mercury. So when doing these gas law problems, I like to read the problem and then kind of isolate which quantities I'm given and assign them to a particular variable. So I've kind of done that here in red. Done that on the next slide as well. Here's the problem along with what those values are and the particular variables written more neatly. So since we have an initial pressure, an initial volume, and initial temperature, we have a final volume and a final temperature. We need a final pressure, so we can use the combined gas law to do that, solving for P2. So I'm going to take this combined gas law and solve for the variable P2 by first cross multiplying to get everything in the numerator. And so doing that, I have P1 times V1 times T2 is equal to T1 times P2 times V2. And then remembering that I need to solve for P2, I need to get it on one side of the equation, everything else on the other. I'm going to divide both sides by T1 V2. And so then that cancels with that. So I'm left with P2 on one side of the equation. So more neatly written, I have P2 as P1 V1 over T2 divided by T1 times V2. And so now I have my combined gas law written in such a way so that I can easily plug in the numbers that I was given in the problem. And I can easily see that my milliliter units cancel, my Kelvin units cancel. I'm left with a value that's going to be in millimeters of mercury, which is great because I'm looking for a pressure, and that's a unit of pressure. And so putting that in your calculator, doing the appropriate multiplication and division. I'm not going to be picky on sig figs here. Technically, it would just be 3 sig figs, but I would certainly accept this. The final answer being 1,253.9 millimeters of mercury. So that's how you would attempt, or that's how you would attack these problems that use the combined gas law.